Alright, welcome to Lab 2, which is the lab all about gravity, and I'm James, and we're gonna get started. Whoop. So, quickly, just going over the introduction, the purpose of this lab is to measure an object's motion from being dropped at rest and observe how gravity and drag force interact with it. And then this motion is going to be compared to two models that are going to be prepared using GlowScript. One will be solely looking at a gravitational force, and then the other will be incorporating drag into this. And so quickly, the results I got is that the graph including drag was more accurate than the one only assuming gravitational force, and we will talk about that very soon. So the fundamental principles that we really need for this is Newton's second law, which is basically just the net force of an object is the change in momentum over the change in time. And this will get us an acceleration value, and so we're going to be using that to basically see if something's moving at a constant speed or if there's actually a non-constant force on it, and that will be used to discuss terminal velocity later on. And then two forces that we need to know are gravitational force, which is the force between two objects with mass. This can be any object with mass, but for the purpose of this lab, it is the Earth and something with just some amount of mass. I ended up using a green tissue, and that is given as the it's in the j hat direction, which is the y-axis, and it's the mass times the acceleration due to gravity, which in the situation of Earth would be 9.81 meters per second, and it's negative j hat because it's facing downward rather than going up in the positive direction. And then drag is calculated as negative b, which is a proportionality constant, times the speed squared in the direction of v hat, but known as the negative, so it's actually moving against the speed. And then finally, the net force is just going to be the gravitational force plus the drag force. So I used Tracker, and like I said, I used a green tissue, and I went ahead and recorded my initial observations and got my time. And so these were the values that I ended up using in my actual GlowScript code. So my mass came out to be 0.02, and my position vector that I got was 0.005, and then I set the origin to be there, so that's why there's a little bit of deviation. Like I said previously, g would be 9.8 or 9.81 meters per second, and then my time condition for this was 0.56 seconds just about, because I had like a little bit of downtime in my actual tracker video. So in order to calculate this, since this is the one just for gravity, W is going to be equal to the mass of the ball, which is 0.02, times gravity times the j hat direction, which is just going to be 0, 1, comma 0. And then we go ahead and just use the velocity update formula, and then the position update formula shown here and here. And then we just update it and iterate until we get to 0.5683. So what this ends up looking like is the position graph shown and the velocity, and we can see that it's a constant slope. But whenever I actually plot this into Excel, I noticed that there was a high deviation, which means this isn't the best model possible. So then we went over to the second one, and the main difference here is going to be actually the introduction to a b constant. And so just going ahead and calculating the drag force is the exact same, but this time we need to do the magnitude of the velocity since we can't actually square the velocity component. And then after we square the magnitude of the ball's velocity, which in this case would start off at 0, but it's being continually iterated and updated, we go ahead and add those forces and then run the velocity update and the position update formulas. And for mine, I got roughly about a b constant because I just did it by changing it slightly over and over and over to be about 0.03-ish. So after doing this, you can see that the position is very similar to it. Quickly, it's nearly identical. And then the velocity is going to be actually very different because it's a non-constant. But this point here, it appears to be kind of flattening off at about negative 2.5 meters per second squared. Not meter per second squared, meters per second. And that's because this is the terminal velocity, which we will discuss very soon. And then after I went ahead and did everything into Excel, we can see that the drag and gravity computational model is a lot more accurate, which makes sense because we would be expected to see some type of terminal velocity or some non-constant velocity. So what does it mean for something to have terminal velocity? And that just means that it's now getting to the point where the force of drag and the force of gravity are canceling each other out. And what that means is that there's a zero acceleration, so we get to a constant velocity. And that can happen at any point. It depends on the b constant and how quickly you can get to it, as well if there is an actual initial velocity of some kind. So for my case, it came out to be roughly about negative 2.5 and super accurately like negative 2.55. Then lastly, so if you went ahead and started it with some amount of velocity, if you did positive, it would take longer to actually reach a terminal velocity because the acceleration of gravity is being a constant. But if you give it an initial negative velocity, it's actually going to approach the terminal velocity much faster. And so, yeah, that's pretty much everything that I need to cover. I hope you guys have a good day. Thank you.